The last problem on the exam did not go as well as expected. And I think out of the whole class, only 4 got it right. And so what I did was I just factored that out. Basically, I threw out that question. Nobody lost points over the last question. But if you happen to get it right anyhow, then you got some bonus points. So that's how the numbers work out on that one. And when you look at the last one, if it's not got any minus this, minus that on it, that's why. Right? There were a lot of possible answers for that, but a lot of people got tangled in trying to meet all those criteria simultaneously. So a little peculiar, I guess. If you go through and add the numbers up, it's not going to look exactly the way it should. But just know it's because that one was thrown out and a few people got bonus points added on back for that. Anybody I missed with the exams? Came in and did not get their exam? Didn't? Oh, guess it's in.
Yeah, that's all right.
It's still there.
Okay.
What we're going to go over today is chemical reactions. We're going to talk about what they are. We're going to talk about balancing reactions, and ultimately, we're going to be working on stoichiometry. This is molar mass, Avogadro's number, those kinds of conversions applied to chemical reactions. But first of all, just as far as what's happening with a chemical reaction, you got some stuff, you put them together, it reacts to make something new. And so in word form, this is a reaction. You take sodium, you react it with sulfur, and the product that it makes is sodium sulfide. So when you're writing a chemical reaction, it's very much a before and after kind of picture. And between the before and the after, you got this, which is a little arrow representing the change that occurs. So everything that's on this side of the equation, which is called reactants, that's the materials you put together to react. Reactants convert into products. So when we're talking about the products of a reaction, we're talking what gets formed. If we're talking about the reactants, that's your starting material, and it's not going to be there at the end. When everything is done, it's going to be in product form. So starting material, ending material. Now, with this particular reaction, if we sort the substances by reactant or product, sodium reacts with sulfur. This is sodium, and this is sulfur. So that's your 2 starting materials. Those react together to form sodium sulfide, and now we got to think about naming system. What's the charge for sodium?
+1.
+1. What's the charge for sulfide? Sulfide is always a -2. So electrically, these don't match. But electrically, they have to match or you don't have a neutral compound. For sodium sulfide to be a neutral compound is going to require 2 positive charges, correct? Therefore, the formula for the compound is this. And that formula Na2S has nothing to do with the reaction. That formula Na2S is coming straight out of your nomenclature system. That's just what sodium sulfide is, no matter what you're doing to it. Question about that formula. It comes based on the charges. Now we have the chemical reaction. Sodium reacts with sulfur to make sodium sulfide. But there's a problem with the reaction as the way it's written right now. And it's that law of conservation of matter thing we talked about on day 1. Because this says you end up with 2 sodium atoms, but it says you only start with 1, and that's not possible, correct? You got to end with the same number of each element as you start with. Because you don't create any new matter, you don't destroy any matter, all you do is shuffle the deck, so to speak. You have exactly the same atoms at the end as you do at the beginning, same numbers, same kind. They're just going to be bonded in different ways. So really, if you're going to wind up with 2 sodiums, you got to start with 2 sodiums. And the way you account for that in a reaction is putting a 2 in the front here to say 2 sodium particles. Now, do you see that that gives you 2 sodiums on each side of the reaction arrow and 1 sulfur on each side of the reaction arrow? Okay. Now, there's a huge distinction between a 2 out front and there's a 2 as a subscript. Notice I did not come over here and do this. But that looks more like what we got over there. But it's not valid because subscripts are internal as far as what the formula of that compound has to be. This 2 came from charges. That's the proportions you have to have internally for that to be a neutral compound. But if we had a 2 here, that would be saying that we had 2 sodium atoms bonded together. That would be an internal thing. And that's not the way it is. Sodium is not a diatomic element like that. We've got 2 separate sodiums, and so we write it with a 2 out front. There are some elements that are diatomic. This is them. These 7 elements are so very reactive that even if there's nothing else around to react with, they react with each other. And they pair off and form what's called diatomic molecules. Diatomic, the prefix di meaning 2. 2 atom molecules. These atoms are diatomic. The rest of them are not. And that will come up every now and then when we're writing these reactions. But when you're doing the balancing, once you've got all your formulas set, then you never tamper with subscripts after that. And you always do it by putting these coefficients out front. And if there is no coefficient out front, then I guess that's implied to be a 1. So 2 sodium atoms react with 1 sulfur atom to make that sodium sulfide molecule. All of this winds up being 1 particle. So coefficients out front are external, subscripts within the formula are internal. Question about that? All right. Do this one. Aluminum reacts with bromine to form aluminum bromide. There's a lot to think about when you're putting these together, because you got to know the symbols, you got to know who's diatomic and who's not. You got to be comfortable enough with your naming system to put those formulas together. What's aluminum? Symbolize. And what's bromine? Is it one of your diatomic elements? Yes, it is. So as the pure neutral element, it's not Br, it's Br2. That's just the natural way it occurs. To form aluminum bromide, what's the charge of aluminum? +3. What's the charge of bromide? -1. So what's the formula for aluminum bromide? There you go. Br3. And in skeleton form, that's your equation, because you got everybody there and in their proper formula. Yes?
Since bromine's diatomic, would it have a charge of -2?
It's only diatomic as the neutral element, emphasis on neutral, okay? So when you're starting over on this side, it doesn't have any charge at all. And once you get into a compound, you can have any number because then it's charged, okay? So this has only got 1, this has got, well, that's chlorine, but anyhow, it's got 2, this has 3, you can have 4 or 5 or however many, because at that point, you're dealing with Br negative, and that's not diatomic, okay? The ion is independent, and 1. It's only diatomic if it's neutral. It's the neutral element, meaning it's by itself, okay? I don't know if that's answering your question or not. Other question with this? All right.
Will you give us things like this where we have to come up with our own formula, or will you give us a formula and just have us balance it?
It depends on the formulas. If it's small formulas like this, I will give it to you in word form. There will be some amount of that. But there will be others. The more complex the reaction, the more likely I am to just go ahead and give you the formulas. Then we need to balance this. 1 aluminum on the left, 1 aluminum on the right. That looks good. 2 bromines on the left, 3 bromines on the right. That's not so good. We got to make those to be equal, though. And comparing 2 with 3, what's your lowest multiple? 6. So we make both sides. If we multiply both sides up to be 6, we can balance that. We'd do that by putting a 3 here, because 3 times 2 would be 6 bromine. And a 2 out here would make 6 bromine. And that balances bromine. But now we got to fix aluminum, because when you put that 2 out front, it affects everybody in the formula. So now there's 2 aluminums, which we've got to account for here. We'll put a 2 there. And that would be balanced. Because you got the same number of each element on both sides. A question about that, about balancing. There are some patterns for balancing that are usually helpful. There's not really any rules other than just the number of atoms has to come out. We're going to look at some more complex reactions. But generally speaking, it's best to start with your biggest compound and try to make things match with it. And it's generally best if you've got an independent element like bromine or aluminum or oxygen, or just an independent element by itself, not a compound, but an element. It's generally quicker if you just leave that one till last. Because whatever you put in front of it, it's not going to affect anybody else. So those make good, very good stopping points. But it's really trial and error. And inspecting things until you know that they match up. Balance this equation. got 3 compounds and an element, it'll probably save you some time to let the oxygen wait till last. It's not a requirement, but it's typically convenient. So you're counting atoms and you're putting in multiples. Always thinking in multiples. And for no particular reason other than it's on the end close to me, let's start with carbon. What are you going to do to fix carbon? You got 10 compared to 1. Not a whole lot of choice, right? What are you going to do? 10. What are you going to do to fix hydrogen? 4, because there's 2 hydrogens in every water. So 4 waters would make a total of 8 hydrogens, correct? All that leaves now is oxygen, and on the product side, we've got 20 oxygens right here, and 4 more over here. So on the entire product side, there's 24 oxygens. We need 24 over here. So what goes here? 12. And that would be your balanced equation. Question about that? We're going to balance a few more, then we're going to go into stoichiometry. And the stoichiometry is based on this. That with these numbers that you've got out in front of these formulas, you're never going to see units written on those, but they do have units, and the units are moles. So this is saying that 1 mole of C10H8 would react with 12 moles of oxygen, and it would form 10 moles of carbon dioxide and 4 moles of water. All of that is in mole units. Balance this one. If you start with vanadium, then this is the first step. You don't have to start with vanadium. There's no definite one to start with. But that would fix vanadium, correct? Let's fix nitrogen. How would you fix nitrogen? 5 in front of the ammonia. And then let's fix, I don't know, hydrogen. How would you fix hydrogen? It's multiplication, so 5 times 3. And then let's fix chlorine. We've got 15 chlorines here. And we got 3 of these, and each one has 5 chlorines, right? So that's 15 chlorines. So chlorine's already okay. And then oxygen, 4 times 15, that's 60 oxygens. And this is 5 times 4 is 20 times 3, 60 oxygens. Question with that? If there is, please ask. Balance this one. When you just scan through that, you've got 5 formulas to deal with, correct? And just looking at those, you've got one substance on the left that has aluminum and one on the right. One on the left that has hydrogen, one on the right. One on the left that has chlorine, one on the right. But oxygen is in 3 of those formulas, correct? And actually, in the notes, the one above this, 5 formulas, 4 of the 5 involve oxygen. When you've got a formula, when you've got an element that's in multiple formulas like that, that's generally one to avoid. The best method for that is you do the other atoms first and you hope for the best. Usually it will work out. Like in the last one, what was it? The chlorine and the oxygen just fell in place. When we took care of the other elements, those elements just kind of fell in where they needed to be. More often than not, that will happen. So, sticking with the hope for the best strategy, I'm going to avoid oxygen and do all the others first. Let's start with aluminum. How would you fix aluminum? 2 here. And then that gives me 6 chlorines. How can I fix chlorine? 6 here. And that gives me 6 hydrogens. How am I going to fix that? 3 water. And then carbon, I've got how many carbons here? 3, because that multiplies in. This part here is 3 carbons and 9 oxygens. So I got 3 carbons on this side, I need 3 carbons on this side, that becomes a 3. And so while balancing everybody else, hopefully oxygen fell in place. There's 9 oxygens here. I've got 3 oxygens in the water and 6 more from there. So yeah, that worked out fine. Question with that? Yes.
In the one we just did with the 1.5 grams of it, you multiplied, or maybe I didn't see this right, but it's the 3V times the 0.4 times the 5. But in this one, you didn't. Is that because it was a coefficient instead of a subscript?
What was the formula?
3V ClO4 5.
Okay. So for the chlorine, when we multiply this 5 in, that's 5 chlorines and 20 oxygens, even before you do this 3. Okay. And so if that's 5 chlorine, 20 oxygens, and we multiply that by 3, it becomes 15 and 60.
But that's because I was coefficient, that's a subscript, right? I wouldn't.
Well, this subscript works the same way as this subscript did.
But I'm not multiplying that times the 2 on the
No, this is not a coefficient. This is the subscript on the aluminum. The coefficient here is just a 1. Okay, so this 3 belongs exclusively to the parentheses, and this 2 belongs exclusively to the aluminum. But what's in front belongs to everybody. It distributes across everybody. All right, so there's our balanced equation. And now we're going to start doing some of the stoichiometry with it. Calculation number 1 in the notes. We've got 2 reactants, hydrochloric acid and aluminum carbonate. And if you put the 2 together, then you'll make those other products. So the question is, if we start this reaction with exactly 10.0 grams of aluminum carbonate, and it says excess HCl, so that's just telling you you got more than enough HCl to make sure that all of that 10 grams aluminum carbonate gets reacted. You've got an unlimited supply of HCl, but you've got a limited supply of aluminum carbonate. If all that aluminum carbonate reacts, how much water can be produced? And the key to the calculation is these coefficients that we've already said are in units of moles. We're trying to relate this, which has a coefficient of 1, to this, which has a coefficient of 3. Now, if you do this reaction and you produce water, you also produce carbon dioxide and aluminum chloride, correct? Because that's your other products. But at least as far as this calculation goes, we don't care about those other products. We're just trying to relate these two. And we're going to relate them by a 1:3 ratio, which is in units of moles, which means the first thing we have to do is get this aluminum carbonate out of grams and into moles. The conversion from grams to moles is molar mass. So we go to the periodic table, we add up all that weight. That's the molar mass of aluminum carbonate. That's 2 aluminums, 3 carbons, 9 oxygens. That's the molar mass of the compound. So that allows us to convert out of grams of aluminum carbonate into moles.